in h bar also in my formulas. And you know also how to describe probably these kind of processes because you can do perturbation theory. So perturbation theory, this is the time-dependent Schrodinger equation, where here you have the kinetic term, here you have the Coulomb interaction. Let's assume, for example, we have a hydrogen atom, then it would be just minus 1 over r. And here we have the light field in some gauge, maybe in the length gauge or in the velocity gauge. And if the light field is weak, then we think about this one as a small perturbation as compared to these terms over here, especially to this Coulomb interaction. So this interaction is much weaker on the electron than the Coulomb interaction. And then we can do perturbation theory, and you probably have done this. And you can write down a transition amplitude where you come from an initial state, which is now a solution to this reference Hamiltonian, to a final state, which is also a solution of this reference Hamiltonian. And for this kind of processes, for example, the initial state would be the ground state of the atom, while the final state would be a continuum state of the atom. And for the hydrogen atom, you know these function exactly. For other atoms, molecules, you would write them down at least approximately. And the perturbation comes here as an operator in the middle, and this is your transition amplitude. Now this is a description of Einstein's photo effect. Now if you have a nowadays laser, the frequencies of the lasers are usually not large enough, or not large enough so that they exceed the ionization potential. So what is happening then? So what is happening if you have the frequency of the light smaller than the ionization potential, so the difference between the continuum and, let's say, the ground state. Now here I make up the case where it looks like that if I would add another photon here, I could make a 2-photon absorption, and I would end up in the continuum here. So that, since our first order perturbation theory gave me the absorption of a photon, actually it gives me also the emission of a photon, where I didn't look at, but it gives me the absorption of a photon. Well, it tells me that probably if I look into second order perturbation theory, I could maybe describe a second order perturbation theory at 2-photon processes. So let's try to do this without going through all the math. But here again, we are considering the light field as a small perturbation. We are starting from an initial state, going into an intermediate state here. Actually, we go into an intermediate state that we write as a superposition of all the states that we have, all the solutions that we have to this reference Hamiltonian. So that could be a sum if it's a discrete spectrum only, or it's a sum and an integral if it's a discrete and continuum spectrum. So then we go via the interaction with the light field into this intermediate state. Via another interaction with the light field, we go into the final state. And the final state, we would assume that lays in the continuum. So that is the second order transition amplitude. So let's try to understand this a bit more. And I'm writing it's now just this first term here, so everything that starts from here up to here as a state which I call a virtual state. So I just rewrite this, call this a virtual state, and put everything that we had before here with the sum and one of the integrals, and call this whole thing a virtual state. Now is this really a state what I've written down here? Well, this what I've written down here, that is a matrix element, so that's a number. And that's a state here, so a number I can always theoretically put in front. So I've just switched the whole two things. And now you see it's really a state that I've described here, because I've written this state, and I can write any state a particle is in, as a superposition of all the solutions of my reference Hamiltonian. And this is nothing else what I've done here. This are my expansion coefficients, and then I have the sum, and if you want the integral, over all states, all solutions to this reference Hamiltonian. So I've described a kind of what I call a virtual state here, and you see it has made a transition into this virtual state, and then a transition from the virtual state into the final state. So we see really from this second order transition amplitude a physical picture now that we have a transition for a 2-photon ionization or 2-photon absorption, where first one photon is absorbed, the system goes into such a virtual state, which I can describe like this. second order perturbation theory she told me. And from this virtual state now, I can absorb another photon and I go into the continuum. I have a two-photon ionization process or a two-photon absorption process. Now this was described by Gerhard Meyer already in the 1930s, but it was the first time observed, not in the 30s, it was the first time observed in the 60s. Why is this the case? Well, if you would do a bit more math here, a bit more algebra here, we would be able to get something like a lifetime of this virtual state. And this lifetime of the virtual state is proportional to the inverse of this energy. Now what is the energy here? So here is the initial energy plus omega. So this is the energy of the initial state plus omega. So obviously what I've written here in the round brackets is the energy of the virtual state. And here what you see is the difference of this energy of this virtual state to all the other states, to all the real states, to all the reference states of my reference Hamiltonian. So the lifetime of this one is inverse to this kind of energy difference, and certainly the longest lifetime I get now, as you see, from difference to the closest state here. Now you can calculate this. This is very short. So this virtual state has a very, very short lifetime. So this means that I need a very high photon density. So that's why I make the transition into this virtual state. There's a second photon that I can absorb from the light field to make a transition then from there into the continuum. So I need a high photon density, and that's why I need a laser. I need a high intensity of my light field. And that's why this process cannot be observed with normal light, like you can do it with single photon ionization, but you need a laser to this one. And that was one of the first applications of a laser that people have observed this type of two-photon photoionization process. Now, you can think about this. Certainly, if I make second order perturbation theory, I get two-photon absorption. What do I get when I make third order perturbation theory? Get three-photon absorption, four-photon absorption, and so on. So I can get multi-photon absorption with this one. Still, I'm treating my light field perturbative here. So I can make a multi-photon absorption process here from the ground state with a laser into the continuum just by considering relatively weak light field still, weak laser field, where the photons are absorbed step by step here into the continuum. Now that is treating the whole thing with perturbation theory. Now the question is nowadays here, they are claiming always that the interaction with the light field is non-perturbative. So somewhere this perturbation theory must break down. So where does it break down? Well, that is the lowest order term that I show you here, how I come with this frequency into the continuum. Well, in perturbation theory, I can go into the next higher order, and actually this is the next higher order that is contributing to this energy level. And I come just to this one by absorbing, let's say, n photons, absorb another photon and emit a photon. That would be, if this is the nth order, this is the n plus second order term in my perturbation theory. So I can write down my series. That is the lowest order that is contributing to this ionization process. Now I come to the next order. It's actually two orders further. Another absorption of a photon and emission of a photon. See, each order, as you have learned from simple photoionization, perturbative photoionization, you always have a term where you have an absorption of a photon or where you have an emission of a photon. Or I have first an emission of a photon and then an absorption of a photon. And actually I can do this at every stage. So when does perturbation theory now breaks down? Well, perturbation theory breaks in that moment down when these two terms become comparable. Because perturbation theory should be something that converges. So my first order term, so my lowest order term, should be much larger than my next higher order term, and next much larger than the further higher order term. So I should compare these two orders and think about when they two become comparable, and get from this one a description, a limit when perturbation theory breaks down. So one can set these two terms equally, and I don't want to do the kind of algebra with you, but you're looking just at the matrix element and the terms that you're adding due to the absorption and the emission of a photon, and you come to a rather simple formula after some approximation, where it scales with the intensity divided by, this is the atomic intensity just, times 1 over 2 omega squared here. And also scaled, this makes it just in atomic units. And this has to be equal to 1. Then the lowest order term is equal to the next higher order term. Now that is a quite interesting relation that we find here, because it tells us something. I have a certain laser of a certain frequency, and it gives me an upper limit of up to which perturbation theory should work. And beyond this, perturbation theory should break down. So below the certain intensities, I can consider my light field as perturbative, as something like weak, as compared to the Coulomb interactions. While if I am above a certain intensity, according to, let's say, this kind of formula, I should consider my light field not longer as a weak field, but I should have considered as a strong field, whatever I have to do that, and we will explore what we have to do. Now, this means I've written this down now, where the lowest order term is actually exactly equal to the next higher order term. Now, perturbation theory actually should break down already, not when they are equal, but when they are approximately equal. So I explored it on the next term a bit, this non-perturbative intensity regime, this limit for this intensity now, where I'm not setting this equal to 1, but I'm setting it equal to 10 to the minus 2. So I say that the next higher order term is 1/100th of the lowest order term. So it's approximately equal. So and then let's look at some kind of different laser systems that nowadays are available. So many of the physics has been done in recent years with titanium sapphire laser systems. So that's 800 nanometers, or if you have, our formula goes with frequency, so we convert the wavelengths into frequency, is about 1.55 electron volts. And then you can put this in, and you get as an intensity, when this formula is fulfilled, that perturbation theory should break down almost at 10 to the 14 watt per centimeter squared. So if you're driving your laser field at an intensity which is lower than 10 to the 14 watt per centimeter squared, at 800 nanometers, then you can treat, at least this formula tells you as a rough estimate, you can treat your light field perturbatively. It's a small perturbation as compared to the Coulomb interaction in an atom or a molecule. But if you're above this intensity, you would expect you cannot further treat it perturbatively. So this interaction of the electron with the light field should be as strong, or should make comparable effects like the interaction of the Coulomb fields inside the atom or molecule. Now this certainly changes with, if I go to different frequencies, and nowadays, if you would have started something like 10 years ago or 15 years ago, you most likely would have done work only with sapphire laser systems or in this frequency regime. Nowadays there's a lot of emphasis, for example, on with infrared laser fields. So let's say some of these lasers work at about, let's say, 4 micrometer. Now this is 0.3 electron volts, and you see the intensity is certainly changing a lot, and you would expect that perturbation theory is breaking down as something like 5 times 10 to the 12 watt per centimeter squared. So it's a much lower intensity already. So that is not the universal intensity, but it's changing. And if you work with X-ray lasers, and I've just taken one number out of this one, 1 kilo electron volts, then you can go to much higher intensities where you have the limit between the perturbative to the non-perturbative intensity. So everything what is below these kind of intensities, as a very rough estimate, it's always only an order of magnitude estimate, you can treat the light field at these different frequencies perturbatively. If you're above this, you have to treat it non-perturbatively. So what happens if we are in the non-perturbative intensity region? there should something happen unexpectedly, what we have not seen before with perturbation theory. And actually the first signature of this one was seen in the 80s by Pierre Agostini and co-workers, and it's something what is called above threshold ionization. And this is a multi-photon process where the atom, or in this case the xenon atom, with a laser at about 2 electron volts, and you see they're operating at 8 times 10 to the 12 watt per centimeter squared, makes a multi-photon transition into the continuum. And I would expect, well, the electron is escaping with, oops. Oh, we have to go the quick way. Here we are. It would escape with a certain energy here, and I can calculate this one. That would be n times omega. In this case, it's a 6-photon ionization, so it was 6 times omega minus the ionization potential. And I would calculate that it gives me this peak. But in the experiment, they have measured the photoelectrons that they have measured as a function of energy, so they have measured which energy they got. And they saw not only a peak here, but they saw also the next peak here. And the difference between the two peaks in energy was just 1 omega. Yeah, so obviously, the atom has not only absorbed in one process 6 photons, but to get this energy, it has to absorb 7 photons. So it has to absorb 1 photon above the threshold. That's why it's called above threshold ionization. Now you would expect, okay, this maybe I can describe also with perturbation theory. And I would expect that the probability for this process to absorb, let's say, 7 photons should be smaller than absorbing 6 photons, and this is exactly what I see here. So you would say this is not a real signature, maybe. Well, if you really calculate it, you would expect that this peak is much, much smaller. But if you're not convinced, then you just do the next experiment, and very quickly after this, people have done the experiment, they have cranked up intensity even further, and they have first 2 peaks here, and then they saw 3 peaks, and then 5, etc., etc. Now, even about this one, you would be maybe not convinced and say, this is still maybe I can explain perturbatively, but look at the height of the peaks. So here, everything is still in order. Let's say the absorption of n photons gives me this peak, 1 photon more gives me this peak, and the absorption probability is smaller, as I would expect for perturbation theory. If I go in higher and higher orders, my probabilities should become smaller and smaller. But if we crank up the intensity further, suddenly something funny happens. This peak, the probability to absorb n photons is smaller than the probability to absorb n plus 1 photons, and n plus 2 photons, and n plus 2 photons. And it goes on like this one. So we get funny shapes here. And sometimes these peaks are more or less even on a similar hub. So this is clearly a non-perturbative effect here that you see here. And you're in an intensity regime where we have just crossed more or less this kind of limit. So we were not at 1.55 electron volts, but we are at 2.34 electron volts. So we have just crossed this kind of regime where we come from the perturbative limit to the non-perturbative regime. And this is one of the first effects where you see an effect where the light field becomes non-perturbative, and non-perturbative phenomena of strong of electron laser field absorption. And you cannot treat the laser field anymore as small perturbations. If you look in the literature around the 80s, you find a lot of these kind of examples. So these are not single experiments. That was actually the first one. This is a bit later, but you see a lot of these kind of experiments, which gives you is a kind of start of the non-perturbative multi-photon ionization. Now, how can I treat this problem? Before I was treating it very nicely by looking at my time-dependent Schrodinger equation, and here's my Hamiltonian, and I had the kinetic term, I had the interaction with the field, and I had the Coulomb interaction, but we're down now for the simplest system that I can think about, the hydrogen atom. And I was saying, okay, this interaction is small in its effect as compared to this interaction. It's a perturbation, and that's why I could do perturbation theory. Now my problem is, obviously, this one is no longer, I can no longer consider this one as small as compared to this one. Now, unfortunately, also this one is not small as compared to this one. So I have two interactions more or less of the same structure. So what shall I do? Try to find an analytic solution. That's a nice gradient studies, but many people have tried already. Up to now, there is no analytic solution from this kind of time-dependent Schrodinger equation. Yeah. So if you have the interaction of our simplest system that we have, the hydrogen atom, then we have only this kind of very simple Coulomb interaction, and we have the light field, you cannot find an analytic solution for this one. Well, nowadays, and I will show you some examples, you can solve such a problem ab initio on a computer, on a grid, make numerical simulations of this one. But in the 80s, you could not do this. So let's try to explore a bit what we could do. Well, you know already if I take this part away here, so the whole light field, for the hydrogen atom, I'm left over with the kinetic term and the Coulomb interaction. Well, you all know that you can solve it, and you all have done it. So an electron in the field of the nucleus, I have a solution. If I take away this term, the Coulomb interaction, then I have, what do I have? I have a kinetic term, and I have the interaction with the light field. That's a free electron in a light field, in a laser field, let's say. Also for this, there exists an analytic solution. So if I take away either this term or this term, I find solution. Yeah, and the solutions that I find if I take away the Coulomb interaction are the so-called Volkov waves. And I would like to show you how they look like. This is actually not new, but the Volkov states are from 1935. So that is a problem that has been solved very early in quantum mechanics. So if I take away just the Coulomb interaction here, I'm left over with something like this one. And I've forgotten to take out the m here. So it's p squared over half. This is the kinetic term. And I have the laser interaction. So I have a free electron in the laser field. That is quantum mechanics of this one. And one can solve this. Volkov has done this in 1935 already. And it looks like this. So it has something that looks very similar to our plane wave, which we would have if there would be no laser field. But I have a kinetic term here. I have a phase here, which is not k squared over 2, but I have k minus a over c. Yeah, so this is, I'm just replacing the momentum by k to k minus a over c. So that is the simple thing. And if you can then do sort of mathematical tricks, and you can write it down also in this form with the help of what is called generalized Bessel functions. These are funny things. You maybe know the simple Bessel functions. So the generalized Bessel functions are just a sum over these over a product of Bessel functions. I can calculate them on the computer. They are depending then on the amplitude of the vector potential of the field and the momentum of the electrons. And you can write it in this nice form because this is a kind of expansion coefficient now, these generalized Bessel functions. And then you have this plane wave form, and you have an energy term now here, which is not longer k squared over 2, like for a plane wave, but it's k squared over 2 plus a term what we call the quiver energy or the conformative energy minus n omega. And you see n omega that looks like n times the photon energy, and I'm summing up over this n from minus infinity to plus infinity. So I'm in a superposition of all possible states here where I have k squared over 2 plus up minus 0 times omega plus minus 1 times omega, 2 times omega, etc., etc. So I'm in the superposition of all these kind of different states. This is what the Volkov states tell me. Now, if you write it down, you see the funny things like this, which looks first completely unknown to you, like this alpha 0 and the up. And what is this? You can understand best if you look at this problem now, not quantum mechanically. So this is the free electron in the laser field quantum mechanically, and you have this solution. You can look at this also classically. Well, what is the classical motion of an electron in a monochromatic field? I can write down Newton's equations, which is just the field strength sine omega t. I can solve for this one. R of t is some initial point. Then I have a drift motion here, v times t. The b corresponds to my k here. And I have an oscillation around this drift motion. So I have the real motion of the electron is doing something like this. I have a drift motion and an oscillation around this. And this oscillation goes with an amplitude which is E0 over omega squared. And it has actually, if you average over this one, you see that there's a certain energy certainly in this oscillation. And this amplitude of the oscillation is just this alpha 0 that you have here in the quantum mechanical solution. And the cycle average energy of the oscillation that you have in this oscillation is this what we call the Kuiper energy or the quantum motive energy. So you can make a one-to-one correspondence here actually, or a close correspondence between the quantum mechanical solution and the classical solution. You see the amplitude of this oscillation and the energy of the oscillation appear here also inside the quantum mechanical solution. With here the amplitude and here the energy UP of this oscillation. Now, I've shown you before, we have now this, let's say, the system of the hydrogen atom in the laser field, and we have these two partial solutions. Let me go quickly back. So we have these two partial solutions. I cannot solve this completely, but I have partial solutions. I take away this part, I have a solution. I take away this part, Volkov gives me also a solution. So how can I make use out of this one now? With the help of something similar like perturbation theory. Well, you can develop a theory from this one, what is called the so-called strong field approximation, or the Keldysh-Falser-Ries theory. So nowadays, if you look into the literature, most of the people are talking about strong field approximation. This is just telling you it has been developed over several years by people Keldysh, Falser, and Ries. So I have this kind of problem which I would like to treat, and I would like to use somehow these two partial solutions that I have. Either the solution where if I take away this one, I can describe my electron in the Coulomb potential, or if I take away the Coulomb potential, I have a free electron in the laser field. Certainly only approximate solution to this one, but I would like to describe a photoionization process now with the help of this process, this kind of two solutions. Because if I take away this, the Coulomb potential, I solved it completely, I solved it non-perturbative. So I make use of a non-perturbative interaction of the electron with the field. Now to do this, I have to think for a moment about my process. I want to describe a multi-photon ionization process. So in the initial state, my electron is bound. Now if my electron is bound, maybe it's a good approximation if I neglect the laser field for a moment. Yeah, so I describe my initial state where I have my electron strongly bound. I consider this as a reference Hamiltonian, like I have done in perturbation theory, and I consider this one as the interaction. In the final state, the electron has left the atom. Now at that point, the laser field should be the stronger interaction than the Coulomb interaction. So I'm switching now from this reference Hamiltonian in the final state to this reference Hamiltonian, where I have my electron interacting with the laser field, and I'm neglecting the Coulomb interaction. So in both states, in the initial state and in the final state, I obviously do something wrong. But let's think about it's maybe a good approximation. Here, maybe it's better to neglect the laser field, while in the final state, if I want to describe ionization, it's better to neglect the Coulomb. As I said, I cannot solve it completely. I have to do some approximation. Yeah. So I'd like to try to convince you that maybe this is a reasonable approximation that you can do. Now you can do something very similar like we have done before in perturbation theory. We use this one as the initial state and the Volkov states as the final states, and write down the transition amplitude. Actually, you can derive this correctly, look for example in the work of Howard Rice. This transition amplitude where you come from this initial state where you consider non-perturbatively the Coulomb interaction to this final state where you consider non-perturbatively the laser field. Now you have considered at different stages of the problem both of the interactions completely. So this is a kind of non-perturbative treatment of my atom in a strong laser field, approximately. So.
And what states do you use for the intermediate state?
I'm doing here nothing in the intermediate state. It's a first order process that I'm doing here. This is no longer perturbation theory here, strictly speaking, because I'm treating in the final state the light field not longer as a perturbation. I have a new series that I've written down now that I would be able to continue here, and this is the first order term from this one. And let us see now what the first order term gives us. Yeah.
Why isn't the Coulomb interaction comes in the same place but the laser interaction?
Oh, that's a good question. I could do the same thing also by putting the Coulomb interaction here. This is what we are doing here is what is called so-called S-matrix theory. And there is a so-called prior form of S-matrix theory and a post form of S-matrix theory. If you do the prior form of S-matrix theory, the laser field comes here as an interaction. So you take the interaction that you have ruled out here as an operator here. If you do the post form, you would take this one over here. If you do the complete series up to infinity, so if you would go further on, and we do a complete series, the two things agree. In this lowest order, certainly they would not agree, you would have a difference. Why does one treat this one? Because it's easier to calculate. That's the simple thing. Yeah?
Is the light here treated as a classical theory?
The light is here treated as a classical.
What's the difference if you treat it as quantum theory?
Then I would do quantum electrodynamics. We have a different kind of set.
Is there any quantitative difference?
At these intensities that we are talking about now. Yeah. Okay, so this you can write down, and now let's see exactly what it gives us. So, since we have treated this non-perturbatively, maybe we have included everything already. And actually we have, I will not tell you. So, it gives us the following. You can write down now the momentum or the energy spectrum as a rate, as a differential rate, depending on the momentum of the electron, and it gives us this form here, where n is the number of photons that are absorbed. And actually this holds for all number of photons that are absorbed. So I only have to consider this energy conservation. So the energy of my electron, how I will be detected at my at the detector is now having n photons absorbed minus the ionization potential minus the quiver energy. Now remember back to our first step that we did with perturbation theory. There we had a slightly different one. There En, the energy of our electron was n times omega, or in the beginning omega minus IP. This term UP never appeared here. Yeah? So I had to overcome with the energy that I'm absorbing from the field only the ionization potential. This theory tells me now I don't only have to overcome the ionization potential, but I have to give the electron also this quiver energy that it has in the field. Yeah, so you can think about this. I'm shifting somehow the limit to the continuum from IP to IP plus UP. And this is a restricted, it does not tell, this theory does not tell me anything about the N. It tells me only certainly that to observe an ionization process, this term certainly should be larger than the sum of these two terms. Otherwise I would end up below the continuum, and that would not make sense. So to have an ionization process, n times omega has to be larger than this. But it doesn't tell me anything about what is n. Remember back, I'm putting in this Volkov states here, And the Volkov states had this n times omega n, but the n was running from minus infinity to plus infinity. We had all orders in it. Yeah? And that's why all these orders appear here already coming from this lowest order with S-matrix theory. And you see then, well, certainly these generalized Bessel functions appear here again. I have here a Fourier transform of my initial state, and I have some prefactors. Yeah. And it gives me then, I can calculate for each order, so for each number of photons that are absorbed, I would be able to calculate what is the probability, or what is the rate in this case here, for absorbing, let's say, n photons from the field. Or n plus 1 photons, or n plus 2 photons, or n plus 3 photons. And actually, this is in qualitatively, at least, in rather good agreement with what has been observed in the experiments. So this is a kind of non-perturbative treatment of this process of above threshold ionization. I treated in the final state of my problem the laser field now non-perturbatively, because I found a solution where in my reference Hamiltonian I treat the laser field or the interaction with the laser field completely. So I have a non-perturbative solution which I brought here into the final state. Now you can say maybe I can do better, but this is at least one way how I can do it. Okay, so this is a non-perturbative solution of the problem, an approximate solution only. So when should this whole thing becomes effective, and how Rice has analyzed this quite a bit, so that is the R of KFR theory. So here's considered here now, one is this a non-perturbative solution? Well, it should be this non-perturbative solution should become effective when this UP plays here a certain role. So he has compared, he says it should become effective when UP over omega should be approximately 1. Because then, if UP is of the order of omega, that means I'm shifting this ionization potential that I have to overcome by 1 photon energy. Yeah, and also out of this I can make a kind of rule, so that that means that the intensity over 4 times omega to the power of 3 becomes 1. Now, let's be again a bit more conservative and don't put in 1 here, like we have done before when we were looking at the breakdown of perturbation theory, but I put in 10 to the minus 2. So and then if you look at the numbers that we have derived before, and now the numbers that we derived with this kind of thing, and you see we are getting approximately the same number. For titanium, sapphire, almost the same. Even for the mid-infrared, almost the same. Or we think about we are making rough estimates, maybe in order of magnitude only. Well, if we are coming to X-ray laser wavelengths and energies, there's a big difference between this kind of formula that Farhad Faisal has derived and this kind of formula that Farhad Faisal has derived. Maybe at some point we can look into this one, which is the Okay, so that is a non-perturbative treatment. So we have done now, we have explored now what is perturbative multi-photon ionization, where we can treat the light field still as a small perturbation as compared to the Coulomb interactions, that is in intensities which are lower than these intensities. And if we add larger intensities, we come to this phenomenon of measured ionization. And we have seen at least an approximate treatment of how we can treat this type of process at this point. Now, as I told you, with nowadays computers, you can treat this problem of a hydrogen atom in a laser field. As I said, there is no analytic solution, but you can solve it numerically on the computer. And that gives you actually a different kind of view of this one just. So here's a rather old calculation from the mid of the 90s. And I took the original picture because I always like to work with the original picture. It's unfortunately not the best copy of this one. So what they have done is a 1D numerical simulation. So what does it mean? They have taken the real hydrogen atom in this one and written down the time-dependent Schrodinger equation and solved it, but they've taken a 1D. So they have reduced everything to 1 dimension. So this is a hydrogen atom which lives only in 1 dimension. So here's the dimension x. So the wave function in the beginning, what is plotted here is the probability density is sitting somewhere here. This is actually the sharp peak that you see here. And then they are put this into a laser field and solve the time-dependent Schrodinger equation as a function of time now. And what you see is, you see wave packets that are coming out here. So that are propagating to larger distances. Now the first thing that one understands is if the electron is close to x equals 0, which is about here, is that the electron is bound. If it's at larger x, or either in positive direction or in negative direction, it becomes unbound, so it goes into the continuum. That would be the interpretation. Now I see sub-peaks here, so I see that my whole wave packet that I have here in the beginning, due to the interaction with the light field, is breaking up into sub-wave packets. Now since this is a 1D calculation, I can do now something very nice, because I can calculate what is the velocity to each of these, according to each of these wave packets, by just looking at delta x, delta t. So I get a velocity to each of these wave packets, and then from the velocity I can calculate the energies, and I get these kind of energies, which are exactly these kind of ATI peaks that you have seen before. And there is exactly, if I would see it here, one omega in between these different peaks. So in numerical simulations, what we have seen before here, in this kind of theory, that we are absorbing n photons, n plus 1 photons, etc., where we see it directly from the formula. You can see it also from the numerical simulations. If you are looking at these kind of sub-wave packets, you see this kind of thing. Now, theory has not ended here in the mid of the 90s. So I want to show you one of the calculations, at least of the end of the 90s, where there was at that time at least accurate numerical integration of the time-dependent Schrodinger equation, actually I think for the argon atom, and a very high resolution measurement, where they compared now these kind of ATI peaks that you see here. So you see the structures even into this one, but you see this different kind of photon peaks. And you see here the calculation, and you see here the experiment, and actually they were shifted towards each other, because if you would overlap them, you see almost no difference. So you can describe this now very well nowadays with ab initio numerical simulations on the grid, this kind of above threshold ionization process, the kind of one electron problem. You can even move into one of these peaks. You see there's a lot of oscillations in this one, and you see between the experiment and the calculation there's a rather good agreement. So you can describe these kind of effects nowadays very well with steel. Okay. So, but I would like, so this is what I've shown you in the last two slides were exact calculations where you solve the time-dependent Schrodinger equation exactly. Before I've shown you the approximation method. And from both of these have advantages and disadvantages. Certainly approximations methods, we're always missing something. But if you do it exactly, we have the complete wave function, but we have to find a way how to get the information. Now, in the next steps, I would like to show you how out of approximation method, this S-matrix theory, this strong field approximation, you can very nicely understand certain effects of atomic and molecular ionization. But before I do this, maybe there are further questions. So if you ask me, I should do some breaks from time to time. So what we have discussed up to now, or what I've tried to discuss up to now, was the difference between perturbative ionization, multi-photon ionization, and non-perturbative multi-photon ionization, and the effect of this main effect of above threshold ionization, which is a non-perturbative effect, and how you can describe it with numerical simulations or with this strong field approximation, which we also call S-matrix theory.
So not so much a question, but I thought that it might be interesting to draw the connection between this quiver energy and what we just heard in the previous lecture about the dipole energy, because it's really very much the same thing. if you think of the harmonically bound electron as being bound not at all, that is, to have a zero frequency, then you get the exactly this ponderomotive force. The quiver radius is proportional to the induced dipole moment. The quiver energy is just that dipole energy, and it has exactly the same kinds of forms. And in fact, in the early days of thinking about the dipole force, people actually called it the ponderomotive potential.
Yeah.
Don't be shy.
Yeah.
I'm not sure I fully understand how an atom can absorb multiple photons at once, say 10 photons. Like, do the frequencies from each of the photons, when you add them up, do they then correspond to some given transition level?
Yeah. So you can see it, at least I see it very nicely from this kind of formula. So the energy of the electron in the continuum corresponds to n times the frequency of the light field minus UP plus IP. So if you think back to, let's do it simple. Let's think back to photo effect. In photo effect, you just had omega minus IP. That was the kinetic energy of the photon. This theory tells you that you can absorb n photons, which gives you n times omega. Yeah, so if you absorb n photons from the field, that gives you an energy of n times omega. And the kinetic energy of the electron that you are setting free is now n times omega minus IP minus this quiver energy. Yeah, so this formula tells you if you do a non-perturbative treatment, you can either absorb in one step n photons, or you can absorb n plus 1 photons, or you can absorb n plus 2 photons, since we are not restricting the n's. And what is the probability for this one? Well, this you see from the prefactor here. The prefactor gives you the probability that you make this transition. Yeah. And whether this is correct or not, you have to compare with experiment.
Yeah, I wonder what happens to all these contributions to the Volkov state with negative n values. So are they suppressed in some sense by this prefactor of Bessel functions, I guess? Or
well, if you make this,
because consider you're in the ground state of an atom, you cannot give any photon to the light field if we can speak in that language, because the field is not quantized and so on. But obviously you absorb n photons, but there's also the probability of giving photons to the light field because you have this minus m contributions in the Volkov state.
yes, but think about this state here. It's the final state is a free electron in the laser field. It's an approximation. Certainly it makes only sense if the electron is free, so it has to be in the continuum.
Yeah, but if you go
But that means that if you, I don't do the whole theory here now, but you would get a delta function here that tells you that only those, you get all terms, but you have to rule out those terms where this term is not exceeding the sum of these other terms, because that doesn't make sense in our theory.
okay, right.
Yeah. So in the free electron, I have the superposition of all the states, but here certainly only certain transitions make sense. So the others are ruling.
So this is actually a discrete function then.
This is a discrete function,
Okay.
and this is, yeah, that's a good point. And this is what you see here, either here. This is a discretization of my continuum. Yeah, I have only certain discrete energies possible in the continuum. So I cannot reach all energies, but I'm reaching only certain energies. So it's a discrete function.
What's responsible for the width of these things?
This theory that I've shown you is assuming that I have an infinitely long laser path. If I have a shorter laser path, it gives me a certain width. Because I have a frequency spectrum in my laser. If I have a shorter laser path. Yeah.
How do you choose which frequency to use to drive these multi-photon transitions?
I'm sorry, once again.
How do you choose what frequency to use to drive these multi-photon transitions? For instance, I mean, what makes you choose 6, for instance, rather than 5?
In this theory, nothing. I have only a minimum number of photons that I need. I need a minimum number of photons to overcome this threshold. Yeah, so to plug in here some numbers for a certain, you have seen before that the UP depends on intensity and on frequency. So this whole energy rule that we have written down here, or energy conservation, depends just on intensity and frequency. So you have a certain intensity, you have a certain frequency, and a certain atom with a certain ionization potential, then you can calculate how many photons you have to absorb to overcome this kind of threshold here. And then you can absorb more photons. That is the above threshold ionization. Just with different kind of probabilities. Yeah.
But does it depend, for instance, in these transitions, we're using the intermediate levels. If you talk about the old picture.
That is a very good question. Here I don't use intermediate levels anymore. Because this is a first order transition. There are no intermediate levels anymore. So this transition, we don't make successive, we cannot think about a successive absorption of photons by intermediate states. But in the non-perturbative picture, the atom or the electron is taking 6 photons or 7 photons or 8 photons in one quantum step directly from the field. That is the difference, it's a very good question between non-perturbative and perturbative. So in perturbative, we are thinking about these transitions via intermediate virtual states. Here we don't have this, at least according to this theory. We don't have this picture. So we are thinking about this one, the absorption of 7, 8, or 9 photons in one quantum step. Okay. And let me try to go on a bit. Where did we stop? Oops. Okay, so I wanted to tell you a bit more. You could ask now the question that nowadays, well, if we can solve the Schrodinger equation completely, at least for most of the atoms and also maybe for some of the molecules, why don't we do this all the time? Why should we do this approximation method? Because maybe and I would like to show you that approximation methods sometimes at least give you quantitatively a very quick understanding of certain phenomena. And I would like to show you one of the phenomena. By comparing now the ionization of an atom, the multi-photon and above threshold ionization of an atom and of a molecule. Now, if you would do this ab initio numerically on the computer, you would just write down your 2 equations, solve it on the computer as good as you can, and you would get some result. And then you would have to go into your solutions, into your wave functions that you calculate, and try to dig out the information. I would like to do it with you with this approximation method, with this strong field approximation, and see which kind of information we can get from this one. So we have written this down before already. There are some certain additional factors in this which just don't play much of a role. So here's the number. This is the ionization rate, now the total ionization rate. So of number of photons that are absorbed, Kn, UP minus n times omega squared. Then you see again this kind of generalized Bessel functions here, and here you have the Fourier transform of the initial state. And if you remember back, in the initial state was the electron bound in our system. So if I look at ionization of an atom as compared to ionization of a molecule, the only thing that I'm changing according in this approximation method is I'm taking, instead of the Fourier transform of an initial atomic state, I take the Fourier transform of an initial molecular state. All the rest does not change. It's an approximation method, but according to this theory, if I look at ionization of an atom or ionization of a molecule, the only difference is whether I take a Fourier transform of an atomic state, initial atomic state, or Fourier transform an initial molecular state. Not so. That is very easy to compare the 2 different effects. So let's look at what happens to this Fourier transform of a molecular state if you look at a simple diatomic molecule. Well, if I look at a homonuclear molecule, and this is always the simplest thing you can start with, a diatomic, And I'm looking at N2 and O2. These are experimentally the easiest molecules that one can look at, and it's also theoretically maybe the most interesting one. But then I can do the so-called linear combination of atomic orbitals, molecular orbital representation, where I represent my molecular orbital, or my molecular state, as a superposition of atomic states, which are centered at one nucleus or at the other nucleus. Yeah, and I make a superposition of this one, and maybe I have not only one atomic state, but maybe I have more atomic states. And then for diatomic molecules, I have two centers, so I could write this one down also not as a sum over all nuclear centers, but I have just two, so I've written down it now in this form here, that one of the centers is located at minus r ½ and the other one is located at plus r ½ Now, if you look at molecules and look at N2 and O2, there are several differences, but one of the differences is that this has a so-called bonding symmetry and this is an anti-bonding symmetry. Now, that means that these expansion coefficients that I've written down here are equal in sign and magnitude for a homonuclear molecule of bonding symmetry. So here, this expansion coefficient is equal to this expansion coefficient. And here they are equal in strength, but they have opposite sign. So that gives me an anti-bonding symmetry, which looks as a probability density sketch, not probability, as a wave function sketch, either looks like this or like this. Now, if I make this calculation, and I'm using now just the Fourier transform of this one, I find out that this is proportional this rate. If I write down this Fourier transform, it's proportional to the Fourier transform of these atomic states here times the molecular factor. And this molecular factor is not different whether I have an N2 molecule, which has in the highest occupied molecular orbital a bonding symmetry or an anti-bonding symmetry, because it gives me either cosine squared Kn times r½ or sine squared Kn times r². What you see is just different kind of interference effect, yeah, of the two electron wave packets that are coming out from the two atomic centers. So I should have a different behavior now. This is at least what the theory, in a very simple way, is telling me, whether I'm ionizing a molecule like N2 or I'm ionizing a molecule like O2, where the electron is either sitting in a bonding orbital or in an anti-bonding orbital. Now, how could I measure this? When I look at this, it depends on Kn times r. Now, K was the momentum of the photoelectron, and r is the internuclear distance. Now, if I look at above threshold ionization, well, the r is not changing here, but my K is changing if I go to higher and higher peaks. So how does this factor looks like? Well, it tells me that if I have bonding symmetry and I make my K very, very small, this cosine square should go to 1, while if I have a sine squared and my K becomes very small, it should go to 0. So I expect that for something that has an anti-bonding symmetry, which is O2, my spectrum near the threshold should be suppressed, should in principle go to 0, while this one should not go to 0. And this measurement has been done, and it was compared always to a molecule and an atom which have the same ionization potential. You can very nicely compare this because you need the same number of photons to absorb it. And you see N2, which has a bonding symmetry, more or less follows exactly that one of R1, because over this whole regime, the cosine squared is more or less 1. While here the O2 is suppressed near the threshold as compared to its, what we call a companion atom, which has the same ionization potential, like the molecule O2. The molecular ionization is suppressed near the threshold as compared to the atom. So you see, qualitatively, we can, with the simple formula, the strong field approximation, very simply explain this kind of effect. But we can explain it only qualitatively, because it tells us, because our formula tells us with the sine squared, actually this should not go like this, it should go down to 0, and this is not C. This is because we have taken in the final state only an approximate solution. We have taken this Volkov states, and we have forgotten the Coulomb interaction. Yeah, the Coulomb action of the free electron with the atom, or with the molecule that is left behind the molecular ion. And this effect of this Coulomb field, well, this should be as stronger as slower the electron is leaving the molecule. Yeah, so it should have a strong effect somewhere here. So here we, near the threshold, we make a bigger mistake than we do over here. So that's why our theory usually agrees much better here than here. Yeah? So qualitatively, we see this kind of suppression, and we can explain it already due to this kind of interference effect that we should have this suppression in the ionization of O2 as compared to N2, but we cannot fully quantitatively describe it because our theory would say it should go to zero. Yeah? But quantitatively, we have a very good description. Now, certainly, if you do this fully numerically, we can describe this whole thing completely, but it's much harder. You have to find out in a different way what would be the effect of this kind of suppression. Yeah? So this tells us that certain molecules are suppressed, this kind of set of molecules should be suppressed in their ionization as compared to the ionization of an atom. So this is qualitatively, at least we can explain this behavior. Now we should expect this also that this happens at all intensities, and this has been measured before, but as a function of intensity, the ion signal, where argon and N2 have been compared at 800 nanometers, and you cannot distinguish the two curves because they lie more or less, at least on this logarithmic scale, on top of each other. And this is exactly what the theory suggests. This kind of simple theory that we have just discussed. While for O2, we would expect the ionization is suppressed as compared to the companion ion xenon, and that's the same thing what you see also in theory. With a very, very simple explanation that we have behind us. Qualitatively only, but we have explained this kind of effect by certain kind of molecules which we suppressed in the laser field in their ionization as compared to an atom which has the same ionization potential. Now this holds not only true for diatomics, but you can go to much larger molecules. And what people have looked at this is now something, you have talked about saturation intensity. I talk also about saturation intensity now, but it's a different thing. Because we identify also saturation intensity. If you look at these curves here now, you see that there is a very nice increase here up to a certain point, and then you see the curve is bending over. So you could make, on this kind of log-log plots, you can always, well, maybe most nicely you see it here, you can make a more or less straight line through this part, and you can make a straight line through this part. And when the two curves intersect, we call it the saturation intensity. And what does it mean? Why is this curve bending over? This is at the moment where at the center of our laser pulse, the ionization probability becomes 1. Well, I cannot ionize an electron more than an ionization probability of 1. That's why this curve is not further increasing with the same rate. Now, why it's bending over and not stopping here, this is because I have a laser focus. So I have a certain laser intensity distribution over this one. It's the highest intensity in the middle and lower intensities at the outside. So what you see here is only the growth of ionization probability, not at the center, but at the outside. So we call this saturation intensity, this kind of crossing point that you could easily do here by yourself. And if you compare this now, that for certain classes of molecules and atoms, the saturation intensity should be obviously equal. While for other classes of molecules, at least we would predict now, that the saturation intensity for this molecule, like O2, is higher than that one of an atom. And this has been measured, for example, also for C60. And you see here the experiment. So this is ionization of C60 to higher charge states. So this is the saturation intensity C60 for C60 plus, C62 plus, C63 plus, 4 plus, 5 plus, etc., etc. Yeah, up to something like 9 plus, one could ionize the C60 molecule. You know what is the 60? It's this buckyball thing, of carbon. Now, if you do the theory for this one, one finds exact agreement, or more or less exact agreement. But if you compare it to an atom, the atom, the ionization, the prediction for the saturation intensities for an atom of the same ionization potential are completely much lower than that one gets for the C60 molecule. And this is actually also due to interference effects, because you can think of that the C60 is built up out of pairs of C atoms. And each of this makes this destructive interference effect like in O2. And also for this one, you have this strong suppression in ionization in C60 as compared to an atom. And if you take theoretically away all these interference effects, which you can easily do in calculation, then you find again agreement between atomic and molecular ionization. So from this very kind of approximately simple theory, you can get at least a qualitative understanding of the difference between molecular ionization and atomic ionization, which maybe would be much harder to get like from a numerical simulation. But certainly from a numerical simulation, I can get other effects. Okay. As I said, it works only qualitatively, and actually this is a theory that we had developed for N2 and O2, and at that moment when we explained the experiment for N2 and O2, we stick out our head and made also a theoretical prediction. We were immediately shot off. Because we made the prediction that if you compare F2 and N2, because this one is an anti-bonding orbital, and this one is a bonding orbital, we predicted that F2 should be suppressed in ionization as compared to N2, and strongly suppressed. But 1 year later already the experiment was done, and if you look at this one, then these are the N2 data, and these are the F2 data, and this is another set of N2 data. So the experiment shows you that the ionization of N2 is actually not suppressed too, as compared to N2. So we can qualitatively explain certain kind of the ionization of certain kind of molecules, or not of all of them. And this is still a kind of open problem, but most likely this has to do with this, that there are many electron effects play a lot of role in F2. So it's very hard already to get already theoretical description of this kind of molecular orbitals. But for this one, to explain this one, you clearly have to go far beyond, or beyond this quantitative description that I've given you before. Good. So coming away from this one, I would like to go into another topic and quickly explain you now how we come from what I've explained to you up to now was multi-photon ionization. How I'm observing many photons from the field and make a multi-photon ionization process. And at least those of you who have worked a bit in the field or have read a bit about the field already, is that often you explain an ionization process in a strong field with tunnel ionization. And I would like to explain you now what is the transition from multi-photon ionization to tunnel ionization. So I'll show you here two different pictures. So the first one is here, you see the Coulomb interaction, and we consider this as a multi-photon ionization where from an initial state we go into the continuum by the absorption of many photons. Now often you see in the literature, instead of this picture, you see this picture here, where you consider this laser field as a strong electric field, and if you make just a snapshot in a moment when the field is strongest, well, if the field is strong, so this is the field here that I'm showing here with the dashed line, and I make the superposition of this field interaction with the Coulomb potential, what I get is something like that looks like this. So I'm making a tunnel barrier here. Yeah, so I can consider that if I make the snapshot in time, that the part of this wave packet can tunnel through this barrier and can tunnel out here. That would perfectly, if this field would be a static field, certainly. Then it's very easy to understand. Now our laser fields are oscillating fields. Yeah, so what is happening in the laser field is now this electric field is first stands like this, and then it varies over like this and back. Yeah. So the question is now, when is this a good theory? When is this a good picture? When it's a good picture, I have a certain tunnel time here that I need to, that this wave packet is tunneling through this barrier. And if this tunnel time is very small as compared to the oscillation time of my laser field, then this picture should be a good picture. Yeah, then I can describe this one as a so-called quasi-static process. I can consider that this snapshot that I have here is long enough there so that a part of the wave packet can tunnel out here. So this means that the tunnel time has to be small as compared to the laser period. Yeah, so the oscillation time of the electric field in the laser field. Now, in the literature, you see very often that these pictures are somehow separated. And one has the feeling that this somehow has not much to do with this. But actually, from the formula that we have not really derived, but which I at least kind of told you how you get this from the strong field approximation, you can make the transition here. You have to make a lot of algebraic steps, which are not very important. For example, you have to write out this one was an integral representation. In its integral representation, the generalized Bessel functions, you have to write down this one in certain approximations, all fine, but these are only certain approximations. The important step is what you have to do to come from this picture to this picture is to replace the sum here. The sum is telling you how many photons are absorbed. Yeah, so it's a discrete sum as we have discussed before. Either I'm absorbing the minimum number or 1 photon more or 2 photons more, so this is clearly a multi-photon picture that I'm describing with this one. But if this number of n is large, the number of photons is large that I'm absorbing, I can approximately carry out the sum by an integral. So I'm replacing the sum by an integral over the omega. At that moment, I'm losing my multi-photon character, obviously, because I no longer have n0, n0 plus 1, n0 plus 2, but I'm making now a continuous integral. At that moment, I make the transition from here to here. Some further algebra, this is another thing that you always read in the book, needs you that hours to calculate it, certainly, and you derive something what is very known as a tunnel formula. Yeah? Especially these kind of exponents that you find here is always a characteristic of a tunnel formula. You can look back over the days of Landau and Lifshitz. They have calculated this already for a static field. You find this kind of exponentials, which is a clear signature for this that you have a tunnel formula. So you can make a transition from here to here with certain approximations, but the important step is here that you have to replace the sum by this kind of integral. So you make out of a discrete photon picture a continuous picture, and that is the transition that you do from multi-photon to field transition. So these two pictures are clearly connected, and actually part of this calculation of this Bessel functions you have to make in a certain limit here, where again the tunnel time is, which corresponds to this, that the tunnel time has to be small compared to the laser frequency. But these two pictures are clearly connected here. So this, we in principle can consider as a limit of this kind of formula. Yeah, so that's a clear connection between this. There's a clear transition between the two things. So sometimes in the literature when one reads this, one has the feeling, multi-photon, I need one theory, tunnel, I need another theory. There's no connection between the two, but there is a connection here. And you can really understand where is the connection, where you take away this sum and you replace it in integral. And then you get different ionization regimes. So when this gamma factor, which Keldysh has introduced in the 60s already, is, so when the tunnel time is much larger than the laser time, then certainly this tunnel picture should not be true. So that means we are in the so-called multi-photon ionization regime. Or if this one is small as compared to 1, so which means that the tunnel time is much smaller than this laser period, we can describe the whole thing very well by tunnel ionization pictures. So I've shown you a kind of approximation which is very much used at the moment in this field for multi-photon ionization, which is this so-called strong field approximation, explained to you a bit where it comes from with the Volkov states, and made you also the difference between perturbation, perturbative and non-perturbative multi-photon ionization. And then if you're more interested in tunnel ionization, that it goes back to Keldysh in the 60s. A lot of, especially Russians have worked on this one. It goes back to Landau and Lifshitz even, with kind of popular formulas by Keldysh, the so-called PPT formula, the ADK formula. They're all connected with this one, very nicely reviewed by Popov in a recent paper, and it has been further developed by Chilonin and co-workers, who has taken all this work that has been done before for atoms and has brought it to molecules. So you have these kind of different ionization regimes, and then if you have even a stronger electric field, you can suppress this barrier so much that this state lies above the barrier, and then we call this so-called over the barrier ionization. So you will see also sometimes in the literature this kind of distinction. Right? Especially you see the distinction between this picture and this picture. Now I could make clear that you don't need two different theoretical descriptions of this one. These are not, it's not separated, but you see one can make a clear transition from this one to this one. Okay. Yeah. Okay. So coming from this one now, I would like to go into a different step, where I would like to talk a bit about high harmonic generation and of the so-called rescattering picture, but based on this, what I've explained to you before. Now, we have talked a bit before about above threshold ionization, where I have the absorption of many photons, and I come with one electron in the continuum. And if this electron is leaving, then I get these discrete peaks in my photoelectron spectrum. Now this electron is in the continuum, but certainly there's a certain probability that this electron out of the continuum will be recaptured back into my ground state. Now, if I make first a transition into the continuum, give the electron some energy from the field, and then I make a transition back, where the electron has to give back its energy then, and it gives back its energy as a photon, obviously. And this photon has a frequency, obviously, which is then n times the number of photons that I have absorbed. So I've made a transition from the absorption of many low frequency photons into one high frequency photon. So I've transitioned low frequency photons into high frequency photons. What is the process of higher?
Could it give the energy back as more than one photon? As a multi-photon process as well, when it comes back down?
When it comes back down with many photons?
Right.
Not aware of this.
So yeah, I was just curious if this is possible at all, or is it just too weak a process?
I think it's probably someone has calculated it. I've never seen it.
Okay.
So I assume that the probability is very, very small for this. So the probability to give it back as one photon is obviously much higher.
There is no experimentals?
No.
Okay.
I'm not aware.
Thank you.
Yeah. So that is a so-called photon picture of high harmonic generation, which is very much related to what I explained to you up to now. But next week, or if you look in the literature, or next week when Margaret Mullane and others come in, they probably will talk again about high harmonic generation. They will show you this picture, most likely, because this is the traditional picture that you see nowadays in the literature all the time. So high harmonic generation is explained here as a semi-classical picture, as a three-step model. So it's considered of this one that in the first step, the electron tunnels out. And this is the tunnel process that we have just considered as a limiting process of our multi-photon ionization. Then, since the electron is set free in an oscillating electric field, it will first accelerate it away from the atom or molecule, and then, when the electric field changes its sign, it can be driven back again. This you can even calculate fully classically. There's a certain, under which conditions the electron can return then to its parent ion. Now, if it returns to its parent ion, it has gained a certain energy, and this energy it can return then when it goes back into the ground state. So also with this one, we have high harmonic generation. Now you hopefully understand now that there's a clear relation between this picture and this picture. That's the same thing. Yeah, this is also a three-step process. Absorption of many photons, first step. In the continuum, second step. Transition back to the ground state is the third step. So there's a one-to-one correspondence. Here's the absorption of many photons. The limit of this absorption of this multi-photon picture is just a tunnel process, as we have just seen. You have a propagation in the continuum. Luckily, we can describe this very, very classically. We have, one has studied very well, but one can describe this very, very classically. And then we have the transition back into the bound state where this is nothing else in our state. So this is a one-to-one correspondence between these two pictures. Now this picture became very, very popular because it had a very high predictive power. So the semi-classical three-step picture is also called the so-called rescattering picture, because what is happening is that the electron is tunneling out, returns them to the atomic or molecular ion, and gets rescattered here or recaptured here. And that is called rescattering. And this is what you will read or hear a lot about if you study more ionization. I have something like 5 more minutes or so.
Yeah.
Good. Okay. So, and Paul Corkum has then discussed in one of his seminal papers that if you have this kind of rescattering event, certainly the electron can not only be recaptured, which makes high harmonic generation, but it could be also just elastically scattered, and that should make a change in our photoelectron energy spectrum, and it gives you more high energy for electrons than what you would expect without these kind of rescattering effects. That was his prediction. And he explained also with this kind of rescattering picture, gave a simple explanation for how double ionization should occur. So you can think about electron comes back, and if you think now about, let's say, the simplest two-electron atom, the helium atom, so either this electron that comes back gets recaptured, that gives you high harmonic generation, or it scatters elastically, that gives you changes in the photoelectron spectrum, or it kicks out the second electron, that gives you double ionization. So he predicted that there should be these three different kind of and since one can calculate this thing, this propagation thing now classically, putting the electron, just classical solutions, put the electron into the field at different times, and then you can even calculate the maximum kinetic energy, and the maximum kinetic energy is kind of very famous formula nowadays in strong field physics. It's 3.17 UP. It's not pi times UP, but very close to it. So it's 3.17 times this Wilber energy. Yeah? So that tells me also, if I'm looking at high harmonic generation now, well, this is the maximum kinetic energy with which the electron can return. So that is the maximum energy that it can return to when it be captured back now. The maximum harmonics that I can get, the maximum energy of the harmonics, is now obviously 3.17 UP, that's the kinetic energy of the electron, plus IP. Yeah, so that is the kinetic energy plus the difference in the bound state. So I should expect that I have harmonics, can generate harmonics up to 3.17 IP plus 3.17 UP. And I would expect that after this there's a so-called cut of my spectrum. And this has been verified many, many times nowadays in experiment. And actually it has been seen theoretically in numerical simulations even before by Jeff Krause and Kenneth Kuhlander. So they have calculated harmonic spectra here for different, I think it was for helium and helium plus, for different intensities, and they saw always this very strong cutoff, but they didn't derive exactly the formula. At that time they claimed it's approximately IP plus 3 times UP. So nowadays we find this exactly at IP plus 3.17 UP. Now you can do the same thing classically, just classically, yeah.
Sorry, on the previous slide, what were the lines on each of those plots at the bottom?
The here?
Yeah, and then also on the AGI.
Ah, okay, so this is just harmonic spectrum with the cutoff that you're expecting, and this is what you see here. This is the ATI spectrum. The first line is here, the ATI spectrum that you would expect without this rescattering effect. And this one is what you expect theoretically with this rescattering effect. So you get more electrons at higher energies. I come back to the double ionization in a second, but let me pick up on this one here. So you can classically now calculate also what happens if you scatter this one and what is the highest energy that you can get according to a scattering in a photoelectron spectrum. And this is actually, you can get, if the electron comes back, it gets back scattered. And you can calculate this, that the maximum energy that you should get is 10, classically you can calculate this is 10 times UP. And if you make numerical simulations for different, again, for different atoms, for different intensities, you see very closely that there's, again, a very clear cutoff in this one, very close to this classical limit that was calculated. Now, the two things that you see here, I will talk probably a bit more tomorrow about this. So this is, for double ionization, this is the yield that one would expect for single ionization, what you have seen before. This rise here, saturation intensity, then the slower rise here. And this is what one expects for double ionization out of this theory, and I will explain a bit more tomorrow about this one. Okay, so this rescattering picture became so popular among many other things, but because it could very well explain classically here these kind of cutoffs that you see in harmonic spectra as well as in photoelectron spectra due to above threshold ionization. So if I can use 2-3 more minutes, then I can maybe just wrap up here about harmonic generation in ATI. Now, if you go into very, very slow pulses, just a few applications of this one, in very, very short pulses here now, then you have an electric field, if you have a very short pulse, which has only a very few cycles. And then I can generate different kind of fields, which we call either cosine-like or sine-like, for example, where either this maximum of the electric field agrees here with appears exactly at the maximum of the envelope of the pulse, which we would call a cosine pulse, or where the zero of the electric field oscillation appears when we have the maximum of our envelope. This is a sine-like pulse. So there is a certain phase in between this electric field, the oscillation of the electric field, and the envelope, which is called the so-called carrier envelope phase. Now, if you have a very long pulse, this carrier envelope phase does not play a role because your oscillations, the amplitude of your oscillations is changing very, very slowly. But if you have a very short pulse of only 1, 2, 3 cycles or so, it matters certainly whether you have this kind of pulse form or this kind of pulse form if you think about this rescattering picture. Now, if I, for example, send free an electron here, it experiences further on this field here, which is rather weak here at this point before it gets rescattered. While if I'm sending free an electron here, it experiences a much higher field before it gets rescattered. And that's why this results in something like this, that if I'm looking now at photoelectrons that are, if I'm the atom here, if I look at photoelectrons that are going to the right or to the left, there should be, if I have a long pulse, there should be no difference in how many electrons I see on the right or I see on the left. But if I have a very short pulse, I see a strong difference between electrons that are emitted to the left or to the right. And this you see here for different kind of these carrier envelope phases. This is the emission of electrons, let's say, to the left and the other one to the right. And you see between the red and right, they are changing frequently. And you can measure this nowadays in an experiment. Gerhard Paulus has developed this one, the so-called stereo ATI, where he's measuring how many electrons, the photoelectron spectrum of the electrons emitted to the right and those emitted to the left. And you see a clear difference between one. And this is nowadays used for, to measure the carrier envelope phase of a pulse indirectly. As far as I know, it's very difficult to measure this optically directly. This is the indirect way how to measure this one. And they have setting up, they have further developed this now and set up this kind of stereo ATI, really to, in time in principle, for pulse to pulse, they can measure the carrier envelope phase of ultra-short pulses that they have produced. Now you can use this rescattering electron wave packing also to make imaging. That is the next step that you can do. So if the electron leaves out, if it comes back, you can show numerically that it comes back almost as a plane wave, and then you can use this whole thing as an imaging tool. So it scatters, for example, if it scatters as a diatomic molecule, you would expect here interference spectra, and Reinhard Dörner and Volkov have explored this a bit recently, what you can read from these kind of diffraction patterns that you get there. Or if the electron, this kind of electron wave packet recombines on high harmonic generation, then you have again interference effects. And these interference effects now, if you look at the harmonic spectrum, let's say here for H2 plus calculated maybe something like 10 years ago, give you certain dips in your harmonic spectra, which are due just to this kind of interference effects that we have talked about before for the ionization. You have similar interference effect, and now certainly it depends on this, whether if you have linear polarization, whether your molecular axis is aligned with the polarization or stands in a certain angle. So this dip, this minimum is appearing at different harmonic orders. And if you go further on with this one, then you can, there's at least one experimental result on this one, that you should be able to reconstruct the molecular orbital, let's say, from N2, and this is a reconstruction, so-called tomographic reconstruction of this highest occupied molecular orbital from these kind of different measurements here. And this is it looks very similar to what you can theoretically. So you can start using this harmonic generation above threshold ionization to make images of this one. You can go further on, at least as predictions. You can also use this again for C60. You see also these kind of different dips, which are, from which one then you can calculate what is the radius of a C60 molecule. If the C60, for example, would vibrate, maybe I would image this in time. Now, the next I wanted to talk about double ionization. Maybe it's a good point to make a break here. So I finished about high harmonic generation, about threshold ionization. So if you have a question about this one, the last one were just the applications of this. And I start with this tomorrow.
So first, thank you very much. Questions are always, as I said, it's good question, criticism, or even compliments. So don't be shy. Okay? They really will not eat you alive.
So going back to the above threshold ionization, the picture you showed where you were saying that you had this saturation because you reached unit probability for ionization. The log plot showed, at least for some of the pictures, a pretty straight line below that. Now, one would be tempted to say, well, I'll take the slope of that line, and that should correspond to the order of the process. On the other hand, the whole idea of thinking of this as being an order of a process goes against the general non-perturbative picture that you're giving. So what gives?
Yeah, so that's a very good point. If you do these kind of plots are taken in the non-perturbative intensity regime. If you do the whole thing in the perturbative intensity regime, you find also as a function of intensity that as a log-log plot, very nicely linear straight line. And then if you plot a line through this, you find a so-called I to the power of n log, exactly like you would expect, and I can read the order of the process from this one. Here I can do this also, but you find never an integer n. Yeah, so you find here I to the power of, I don't know, 6.3 or whatever. I'm not aware that someone has made a good meaning out of these kind of non-integer exponents that you find. So you find still a straight line, but you will not be able to show that this corresponds to a certain order of process. And that makes sense if you're in the non-perturbative regime, you don't have an order of the process, but you have a sum of many orders.
But it seems odd that it corresponds to, it is still a straight line.
Yes, but I'm not aware of that someone has shown a theoretical explanation, has given a theoretical explanation of this.
And how does that, let's call it a pseudo order for the process, compare to the order of the process you get when you go to lower intensity in the perturbative?
That depends. Sometimes this number is two number of photons larger than the minimum number that you have to absorb. Sometimes it's closer to this one. Yeah. So I've not studied it by myself very well, but I've not seen in the literature any kind of explanation or attempt explanation. Probably, maybe if you go back to the 70s or so, maybe you find something. I'm not aware of. Yeah, but it's tempting. Yeah.
When you're talking about harmonic generation, you say that the electron recollapses back into the ground state. Does it ever recollapse back into an excited state? And
Yes, but the probability and the coherence for this is much smaller.
okay,
So that's why you don't see it.
okay. And also, when you were showing the experimental data, there was, I think it was theoretical plots where you showed it came and it dropped off very sharply, but there was a bit of a tail for the for some of the plots.
Yeah.
For those. Is there a reason for there being a more slanted tail instead of like actual?
Well, classically, you see here that it should stop. Well, quantum mechanically, there's still a probability that you can have higher transitions. So if you go back to this photon picture, it does not tell you that there's a clear cutoff line. Yeah, but so first of all, these are not experimental data, sorry, but these are the mega simulations. But I just wanted to show you the first calculations where this has been found, but it has been shown many times in experiment. But you see, I would call this a clear cutoff because this is a logarithmic scale. So from here to here, the signal has dropped by 10 orders of magnitude.
Okay.
That is a clear cutoff, I would say. Yeah, but the probability does not immediately vanish. Yeah, so quantum mechanically, there is not a cutoff that tells you after 3.17 you peak. Quantum mechanically, the probability is 0 after this. But the probability drops off exponentially.
Okay.
And that is, I would say it's good enough to believe in this classical picture as a good approximation.
Can you use the same non-perturbative method to calculate cross-sections as a function of photon energy?
Yes?
You can. Don't you miss resonances because of intermediate states that are...
If the intermediate states play, the resonances play an important role, then the prediction that I get from my, let's call it simple theory, which is used very often, will not be good. Because I missed something in my theoretical description. Yeah? So that is then the problem that if you make an approximation method, it's an approximation, and it will not hold for all cases. So you have seen also this case for F2, for example, where nowadays it's believed that many electron effects play a role, which we didn't put into the theory. If something else plays a role which is beyond the approximation that you have done, you will see that your approximation does not work, and that your prediction of your theory does not work, which is then a good hint that there is something else, and gives you a first hint that where maybe you should expand to.
So when you are choosing the frequency for the laser DRAM, be careful that any n times that frequency does not coincide with a resonance.
These excited states I've not talked about